This is problem 1 on practice exam 9 of chapter 2 in the book Problem Solving with Differential and Integral Calculus. We have a bungee jumper, and it starts, time equals 0 is when the bungee jumper starts to slow down. So this is not from the jump. The cord has caught, and this is the slow down phase. So the jumper starts at 20 meters per second on the way down, and then this is the cord stopping the bungee jumper in 2 seconds. The speed is 0 after 2 seconds. Okay, so part A, carefully draw a good tangent line at 1 second and get the slope. Let's focus on that. Identify the point on the line, draw a good tangent line, and the rise looks like from 5 to 25 meters per second, and the run is the whole thing, 2 seconds. Pretty straightforward. The slope is minus 10 meters per second squared. The jumper's slowing down at a rate of 10 meters per second each second at 1 second. After that, the slowdown rate's higher. Before that, the slowdown rate is less. Now we're ready for part B. Get the slope of the line that connects the 2 points, 0.9978 and 1.005. So these are 2 points that are very close to 1. It doesn't have to be symmetric around 1. Any 2 points close to 1 will give us a good estimate of the slope at 1 if we connect them. So the normal equation that relates V and T is given. We can just plug in those 2 times. If we plug in 0.9978, the speed is 15.022. And a little bit later, 1.005 seconds, the speed is, it's slowing down. Now it's only going 14.950. We can subtract those to get the difference in speeds, and that's the rise between the 2 points, minus 0.072 meters per second. On to part B. Get the slope of the line that connects the 2 points t equals 0.9978 and 1.005. And then compare it with the slope we got from the tangent line. Any 2 points that are very close to 1, they don't have to be symmetric around 1 second. As long as they're close to 1 second, if you connect them and get the slope between them, it's going to be very close to the slope of the line itself. So the normal equation is this, and we can plug in any t we want. So we're going to start off by plugging in 0.9978 and calculate the speed, 15.022 meters per second. A little bit later, at 1.005 seconds, the speed is 14.950. It's slowing down. The bungee jumper is slowing down, and the amount it slows down is the rise. It's negative, slowing down. We can subtract those two, and we get minus 0.072 meters per second. That is delta V. Now we need delta T to get the run. And to get that, we subtract the 2 times. So 1.005 minus 0.9978 is 0.0072 seconds. That's the run. Now when we use the tangent line, we got a slope of minus 10 meters per second squared. And that's dv dt approximately. So from the calculations, using the normal equation, we got a difference in speed, the rise, of minus 0.072. And the run is 0.00272 seconds right here. And the ratio is minus 10 meters per second squared, as we expected. That was the slope using the tangent line, and that's about the slope using 2 points close to 1 second. Part C, now we're going to get the exact answer, dv dt, by taking the derivative. Here's the normal equation. At some time dt later, the speed is v plus dv. So we substitute those in. We want to get dv, so we're going to square out the t plus dt. We can throw out the dt squared term. It's infinitely smaller than dt. Now we have that. And now we can, here it is again, and we're going to subtract the v from both sides. So v is 20 meters per second minus 5 meters per second cubed t squared. And that whole thing is going to go away. And we're going to be left with dv. So dv is just the 5 meters per second cubed times the 2t dt. And we put the 5 and the 2 together, get rid of the parentheses. We get minus 10 meters per second cubed t dt. For dv, we want to get the slope, so we divide both sides by dt. Now we want to get the slope at 1 second, So we plug in 1 second to our slope equation. And we get minus 10 meters per second squared, which is what we got by taking 2 points close to 1 and getting the slope between them. And we got that same thing, minus 10 meters per second squared, with the slope of the tangent line. So, part D, if we're required to get the slope of the line at 1 second, we need the slope at 1 second to 4 significant digits. What are you going to do? Would you take the derivative or draw a tangent line? And the derivative is exact. It's the slope at the point. So if you want as many significant digits as you need, take the derivative. If you get the slope between 2 points on the line that are very close to 1 second, the results can be as precise as you want. You just got to get closer and closer to 1 second. You can choose 0.99999 seconds and 1 second, and you're going to get the slope between those 2 points is going to be very close. A tangent line requires a good eye, and if 2 people measure the tangent line, the results are not going to be the same to 4 significant digits. It's very challenging to be precise with the tangent line. So if you need precision, get the derivative. It's exact.